In this research, we present a data-driven method for cloth and soft body simulations designed for tightly constrained interactive applications. Our method is capable of producing high-quality, detailed simulation results for thousands of vertices in hundreds of microseconds with just a few megabytes of memory. Subspace simulation techniques have typically been the go-to method for accelerating physics simulation in interactive applications, yet they can have difficulty efficiently modeling the effects of external forces, such as collisions with external objects. In this research, we developed a data-driven subspace simulation method, which uses a neural network to model such external effects efficiently, and produces a simulation which runs entirely in the subspace, with the projection only required at render time, allowing for large performance gains. We start by gathering large amounts of offline simulation data for the object we are interested in simulating. We then apply PCA to this data and project the data into the PCA subspace to build a compressed representation of each frame. Using this subspace data, we construct a machine learning model which is trained to predict the next state of the system given the previous state and the state of any external objects. A naive training of this model results in unstable prediction, so we use a novel training procedure to backpropagate errors through the complete iteration step of the simulation. Once trained, our subspace simulation method is fast, stable, and requires a minimal memory to produce interactive results similar to those in the original training data. Here we show our method applied to two simple setups, a ball interacting with a sheet of cloth and a flat sheet with interactive pins at each corner. The external objects in our system can also include parameters such as the wind direction and speed. Here we show our method applied to a flag on a pole with the wind direction and speed controlled by the user. Our method scales well to more complex situations. Here we show our method used to simulate a cape attached to a character, dynamically controlled by the user using a joypad. Here we show it applied to some motion capture data from a test set. Our method can deal well with complex collisions. Here we show a skirt attached to the character. Our method learns how to model the collision of the skirt against the detailed character mesh efficiently, all while remaining in the subspace. Here we show it applied to some motion capture data from a test set. Here we show our method applied to a deformable bunny pinned to the ground. Our method works just as well for elastic soft bodies as it does cloth. Here we show our method applied to a deformable dragon with a teapot as the external object. The position and orientation of the teapot can either be taken from a test set or provided by the user. By adjusting the number of bases used in the subspace, we can allow for a trade-off between quality and performance and memory usage. Here we adjust the number of PCA bases from 64 to 256 to get different levels of trade-off. However, like all data-driven methods, our technique has some limitations. It cannot reliably extrapolate beyond what it has seen in the training data and can occasionally produce unnatural results in unfamiliar situations. One technique we found to counter this was clipping the inputs and outputs of the system to the minimum and maximum found in the data. Pre-processing time for our system is also very long, with up to several days of computation required for gathering data and training the network. In conclusion, we present a data-driven method for physics simulation design for interactive applications, which combines subspace methods with a machine learning model to produce a simulation which is fast, stable, and with low memory requirements.